Kia ora koutou. This is a request for Alex G, and it's from the June 2020 paper. First of all, there's a division question where we're going to practice long division and the other division method. Then we need to do some integration, and we're going to get an inverse tan thing going on in here. I'm going to do a wee bit of revision on harder inverse tan problems. So I'm just going to do this one using long division. I might start off the second method, but I won't work it the whole way through. So long division here, we need to make sure that we put all of our place value columns in. Right, that's the safest way to do it. We've got 2x cubed minus x squared plus 6x plus 3. And so off we go as usual. We're going to say x squared times what will match me this? Well, it will be x squared times 2x. So 2x times all of this is going to give me 2x cubed plus 0 plus 6x. And I want to subtract all of this. And I get 0 minus x squared plus 0. I bring down the 3. Right, let's go again. What times x squared will get me negative x squared? Well, it'll be minus 1. So we get negative x squared. So now I'm doing this times all of this, negative x squared plus 0 minus 3. And I'm subtracting all of that, which leaves me with 0 plus 0, 3 minus negative 3 plus 6. So the quotient is 2x minus 1, and the remainder, when I divide by x squared plus 3, is 6. And that means that I can write p of x, well actually it's not p of x, I can write the division as, let's see, well we've got, I'll just go back to the start. So what does it mean to say that something is the quotient and something is the remainder? The quotient is this bit here, and then the remainder is simply 6 divided by x squared plus 3. And now we're ready to go off and integrate. I'm just going to show you how we could do that the other way. And this is my preferred way. I think it's slightly faster, but you have to be a wee bit careful. So what we're trying to get to is this in the numerator. So we're going to start by saying, well, it's got to be 2x times x squared plus 3. But I've now added in, let's see what I've got. Well, I've got 2x cubed plus 6x, which is exactly what I want in here, but I've still got minus x squared plus 3. So that equals 2x, and then minus 1 times x squared plus 3. Let's do it as, I'm going to do plus negative 1 there to make that really clear. So here we've got x squared plus 3. Now this is not exactly the same thing, right? Because here I've got negative 1 times 3, which is minus 3, but I wanted to have plus 3. So I've got to add the 6 back on. And that gets me to the same answer, 2x minus 1 plus 6 over x squared plus 3. So I find this method slightly faster, but you've just got to be a bit careful with signs when you're using it. All right, now we're ready to find the integral. And the integral is evaluated at the limits of 3 and 1. So we have this thing here. So this first bit is really easy. For this bit, we need to do a little bit of a detour. You can see that it's going to be something to do with tan inverse. All right, so I'm going to come back to it, but we'll first have a look at the basics of differentiating tan inverse of x. So if y equals tan inverse of x, then dy by dx is equal to 1 over 1 plus x squared. Let's just try a couple of harder ones. If we've got y is equal to tan inverse of 2x, then dy by dx will be, by the chain rule, 1 over 1 plus 2x all squared times the derivative of the inside function. And that's going to get me 2 over 1 plus 4x squared, right? So this pattern here has still got a 1 plus a number. When we look back up here, we haven't got a 1 plus a number. We've got a 3 plus a number. So you might remember when we did the binomial theorem, we had ways of forcing the 1 plus pattern in. And we could do that here, right? But we'll play around with it a little bit more. Let's now try what happens if we've got y is equal to tan inverse of 1/2 x, or x on 2. Well, in this case, we get dy by dx is 1 over 1 plus 1/2 x squared times the derivative of the inside function, which is 1/2. And when you clean this up, you'll see that you get 1 over 1 plus 1/4 x squared times 1/2. Getting a common denominator in here gives me 1 over 4 plus x squared over 4 times 1/2. And fixing that up gives me 4 over 4 plus x squared times 1/2, which is quite nice, and gives me 2 over 4 plus x squared. So this is starting to look like what we've got up here, where we've got x squared plus 3. Right? So what we started with here was tan inverse of 1/2 of x, and we can see that we've got the 2 squared sitting in here. So that suggests that what I should be trying for my integral here is going to be some constant times tan inverse of x on root 3. And that's what I'm going to do now. So that was the brief detour. If you watch the video with all of the tan inverse revision that I did a few months back, or actually maybe last year, there are lots of examples like that one there. So let's get back into this and do the integration. Just find my piece of paper. So the first bit in here is really easy. 2x integrates to x squared minus 1 to minus x. And now let's try, leave a big gap, and we've got tan inverse of x on root 3. Now, when I differentiate tan inverse of x on root 3, what exactly am I going to get? Well, we can work it out down here. If y equals tan inverse of x on root 3, then dy by dx from a similar process to what we just did is going to be 1 plus x on root 3 squared times 1 on root 3. And that's going to give me not exactly what we want, right? But it's going to get me the 3 plus x squared pattern coming in. So now we're going to have root 3 squared, so 3 plus x squared with, what will we have up the top? We'll have 3 here times 1 over root 3. So that gives me root 3 over 3 plus x squared. But I don't want that. I just want 6 over x squared plus 3. So if we want to have no root 3, let's just look at what we've got to do with the constant for our y. So if y is equal to 6 tan inverse of x over root 3, then y dash will be 6 root 3 over 3 plus x squared. So we don't want that. So we can adjust it again. If we have y equals 6 over root 3, then y dash will be, that will all be undone. Okay, so that's a very long way of saying when I'm differentiating this thing up here, it's going to be 6 over root 3 times tan inverse of x on root 3. So if you haven't done the worksheet that I wrote with lots of patterns like this, hopefully watching this is making you realize that it's well worth putting in probably half an hour just to do a whole bunch of tan inverse patterns. Because if you've done them, then this should be reasonably easy. What do I do now? Okay, so we just got to substitute our values in, and we're going to get here, we get 9, 3 squared minus 3 plus 6 on root 3 times tan inverse of 3 on root 3, which is root 3, minus 1 minus 1 plus 6 on root 3 times tan inverse of 1 on root 3. So it's time to crack into the special triangles. Here we go, we've got 1, root 3, and 2. So tan inverse of root 3 is pi on 3, so that's for that one. And tan inverse of 1 on root 3 is going to be pi on 6. So all up, this gives me a bunch of stuff. I get 6 plus 6 on root 3 times the angle whose tan is root 3, which was pi on 3, minus, that goes, 6 on root 3 times pi on 6, I think. Let's see. Okay, cleaning this up lets me finish the whole thing off with 6 plus 2 on root 3 pi minus 1 on root 3 pi, which gives me a nice final answer of 6 plus pi on root 3, just collecting up like terms in here. I can rationalize that if I want, and I'll get 6 plus, what have I got? Root 3 on 3 pi. I think I'd probably leave it like that. Okay, thanks for watching. Now, that probably felt pretty painful if you haven't done the work on tan inverse. So best thing to do now is to go watch the tan inverse video, and I hopefully will see the views for that video go up and know that you actually are taking the advice. Thanks for sending the question in, Alex, and keep on sending them through.